Okay, the third of the videos here, we're going to focus in on the second factor that affects the collisions in between these reactants in a kinetic study is contact area. The fact is A, which is a reactant in a hypothetical reaction, and B have to collide in order to break their bonds. Period. So the whole thing is about these collisions. If they can't touch each other, they won't react. It's real simple. So anything you could do to increase the contact of the chemical. Component A coming in contact with component B will increase the speed of a chemical reaction. The thing is, what are examples of that in our everyday life? So the first example, let's take sugar. Okay, you're going to dissolve sugar in, let's say, some tea. And you go into the cabinet and you have two choices. You have sugar bags, and in the sugar bags you have the small granules of sugar that are crushed up versus sugar cubes. When the chemicals come in contact with the tea, only the chemicals on the surface of the cube are going to come in contact with the tea. And that's important because chemistry is a surface chemistry. When you're dealing with solids, it all happens at the surface. So if the reactants are solids, you have to keep in account surface. Chemicals are going to come in contact on the surface. So anything that you increase the surface area, that means more places where you can get the two reactants to come in contact. So if, let's say, component A is sugar and component B is the tea, anything you can do, and sugar is a solid, anything you can do that increase the tea to sugar contact collisions will increase the rate of the reaction. So in the case of the cube, you only have these four sides to come in contact with the sugar because the rest of the sugar is on the inside of the cube. But meanwhile, here you have small particles, which therefore will have more sugar to tea contact, and therefore the reaction will go faster. And that's a simple analogy of something that we see every day in our life. But let's say you went camping and you wanted to start a fire, and you know that the wood needs to react with the oxygen. If you want to start a fire, you go out and you're going to find twigs. Or how about sawdust? That would really react faster. So if you're in order of wood, sawdust versus twigs versus a 2x4, the sawdust will react faster because by lighting the sawdust, you're going to have more contact between the oxygen and the wood, therefore increase the speed of your chemical reaction. It turns out this phenomenon is true in so many different examples. Let's look at the example of iron reacting with oxygen. If you recall, okay, I showed you an example of a hand warmer. And in the hand warmer, the main ingredient was iron. But what's important to note about the iron in the hand warmer, it was pulverized into a powder. And the reason for that is they needed speed. What they did is they pulverized the iron into a powder. And by pulverizing iron into a powder and adding a catalyst, they were able to generate heat a lot faster. Even though we know this is an exothermic reaction, the key here is to be able to generate the heat very quickly. So by pulverizing the iron, rather than have an iron bar in there, you'll be able to have more iron to oxygen contact to generate the heat. In fact, if you pulverize any substance, you can basically burn it. For example, if even though we know a steel beam will rust if it's not painted, and that is an exothermic reaction, it happens really slow. But if you take that steel beam and you were to shred it into tiny hairs, like that's what steel wool is. If you were to light steel wool, instantaneously it would ignite and become iron oxide as it reacts at a very, very fast rate. In fact, you could start a fire very easily just by lighting steel wool. Another example of the critical concept of contact area in our everyday life. Let's say, for example, you went to the store and you went to the supermarket and you went into the orange juice section. And if you would go to the orange juice section, you would notice that they sell orange juice sometimes in cardboard containers. If you were to get a 1-gallon container, and you would notice they also have pint-sized containers like they used to sell in the elementary schools um, with orange juice in them. And let's say the manufacturer generated these containers on the same day. And on the boxes, they would have an expiration date. Whenever you see an expiration date, that means that the chemicals necessary for the reaction are all present. What do you mean they're all present? Well, inside the container you have acids. The acids react with oxygen. The typical consumer doesn't realize that oxygen is a very small molecule and can go through the cardboard box and react with what's inside. So component A is in the container for the reaction. Component B is outside the container but can pass through the cardboard box to react. If they both had the same expiration date, and we know that the reasons why we drink orange juice, they have vitamin C, which is your absorbic acid. I say to you, if you took a glass from each of these containers of orange juice, the same size glass, you fill them up, and you were asked the question, which one contains more vitamin C? You would first be puzzled. The typical consumer would say, well, wait a minute. Shouldn't they have the same amount of vitamin C? But a chemist who studies kinetics would say, no, they won't. Think about that. Why wouldn't they both have the same vitamin C? Well, that's because there's a kinetic study going on right now. Which one of these containers will have more oxygen to absorbic acid contact and therefore break down the absorbic acid, which is the vitamin C, and would contain less vitamin C when you pour that glass? Well, the winner of that would be the small container. The small container has a reaction that's going on faster. Because the container is small and the oxygen can come in contact with more of the orange juice, the amount of vitamin C per glass would be less if you poured it from the small pint container versus the gallon container. Again, this is because of the surface area of the reaction. Here, the container being smaller will allow more oxygen to orange juice reaction to occur at a much faster rate. Let's say you had a candle and you lit a candle on the top. First thing that people don't realize, is it the wax in the solid phase that's reacting? Or is it the wax in the liquid phase that's reacting? Or is it the wax vapor that's being generated right at the surface of the wick? Based on what I just said about the surface of the wick, I think many of you would consider the fact that the gas, the vapor of the wax itself, is reacting faster than the liquid, than the solid. And we know this because what happens is the heat of the reaction would melt the candle, and the liquid would rise up the wick, on the surface of the wick, vaporize and burn at a much faster rate than the actual liquid and the solid candle. We know the candle overall is disappearing because the solid melts to a liquid which rises up the surface of the wick, and at the surface of the wick, the heat is allowing the wax to vaporize and burn. So what's happening, it's all happening on the surface of the wick. It's all happening on the surface of the wick. So right at the surface is where the chemistry is taking place. Right there. Right on the wick. So here's another example of which phase of matter will react the fastest. Solid, liquid, or gas, and gas is the winner.